Assalamu alaikum. Good morning, everyone. We'll be starting our webinar in 5 minutes. We're waiting for other attendees and for our guest speakers to join. Can you hear me just to make sure? Say Omar.
Alaikum salam. Good morning. I can hear you. Yeah. Thank you.
Great. So I'll be starting with a presentation of our guest speakers. Then I will leave them to present each one his presentation or her presentation, and they will follow up with a brief summary of their respective presentations. I'll just mute and wait to start in 4 minutes. So again, Assalamu alaikum. Good morning, everyone. Should be able to start right now. It's 9:15 local time, Morocco time. I'm Ahmed Sqalis Naji, the moderator of this webinar. Joining me, Mr. Hamza Al-Hashimi, Mr. Omar Al-Alawi, Dr. Rudayna Abu Husn and Mr. Philip Tsang as our esteemed guest speakers for today's webinar. We'll be talking about AI and automation, mainly in Python, applied to geotechnical engineering. The choice of this topic has been matured for a couple of months now, so we are happy to present you a couple of technical presentation on the topic. In Arabic, السلام عليكم. سعيد جدا بتواجد معكم هذا اليوم لإلقاء هذه الندوة حول الذكاء الاصطناعي والأتمتة في الهندسة الجيوتقنية. This webinar is organized by Cercle des Géotechniciens Marocains, Moroccan Geotechnical Circle, in collaboration with Gulf Geotechnical Engineers. So without delay, I will be presenting the speaker presentation session, which will take 1 hour, starting with Hamza, who will be presenting next generation geotechnics hardening automation with optimization and numerical designs, followed by Omar Alawi, who will be leveraging big data for enhanced decision making in maritime geotechnical engineering applications in port and land reclamation projects, followed by Dr. Dana Abul Hosn, the applications of artificial intelligence and machine learning in geotechnical engineering and in engineering, and then ending with Philip, who will be presenting Python automation in geotechnical engineering and tunnels. So we'll start with Hamza. Hamza, you are with us. Maybe you can share your screen. I will leave you the sharing button, and before he can start, I will make a brief presentation of himself and a brief summary of his presentation for those who will want a summary of presentation. So Mr. Hamza El-Hashimi is a lead green associate specializing in geotechnical design and remote sensing. He's the CEO and technical director at Geostructure Bahrain. He also co-founded the Gulf Geotechnical Engineers, the GGE platform. His education includes a bachelor in civil engineering from the University of Khartoum and a Master of Science from King Fahd University. And currently he's pursuing his PhD with over 12 years of experience in geotechnical design and field engineering. Mr. El-Hashimi has contributed to significant projects in GCC, MENA, and Europe, including the world's largest micropile draft, HS2 in UK, Aramco, CSD, US Navy, among others. His expertise covers soil structure interaction, remote sensing, climate change, and advanced geotechnical methodologies. He's also involved in academia as a lecturer, researcher, and author, focusing on innovation in geotechnical engineering. He will be presenting as I said before, next generation geotechnics. This presentation explores the transformative impacts of automation, optimization in geotechnical and numerical designs, highlighting the evolution from traditional methods to modern technology-driven approaches. It addresses the need for these advancements due to inherent complexity and limitations of conventional geotechnical design methods. The role of artificial intelligence and machine learning is emphasized in this presentation, showcasing their potential to enhance predictive modeling, decision-making, and design efficiency. The presentation also outlines the significant advantages of integrating automation, such as increased accuracy, time and cost savings, and adaptability to complex engineering challenges. Finally, it provides insights into future directions and necessary developments, including the integration of Internet of Things, real-time data analysis, and the ongoing evolution of smart infrastructure in geotechnical engineering. This comprehensive overview serves as a guide to understand the current state and future potential of automation and optimization in geotechnical and numerical designs, aiming to equip engineers with the knowledge and tools needed for next generation geotechnical solutions. Hamza, the floor is yours. Thank you.
Thank you, Ahmed. Assalamu alaikum wa rahmatullah. I hope I'm audible. Okay, so I guess yes. Apologies for I'm switching off my camera because I believe my internet connection where I am at now is not super cool. So I hope it will not be interrupted. That's why I switched off my camera. Thank you, Ahmed. It's really great to see the integration between the English and Arabic, the Gulf Geotechnical Engineers and the Moroccan Geotechnical Society. It's joint efforts, and I'm flattered to share the stage with great experts we have today, Mr. Omar, Dr. Baina, and Philip. So as Ahmed introduced, I represent Geostructure and also co-founded Gulf Geotechnical Engineers, and today I am presenting on the next generation geotechnics, and I kept the term or the terminology next generation geotechnics because I want to emphasize that the basic is still required: the analytical, the manual solution, the theory, the concept, the soil mechanics, the numerical designs. All of that has to be there, and then next is the automation and optimization, which is the next generation geotechnics. My resume, but I will skip it after the fair introduction from Ahmed. So let's introduce the topic briefly and simple. I'm sure there are a lot of experts today. They will shed more light and they will go more in details about this. But when we're talking about automation and optimization and numerical design for geotechnical engineering specifically, we are talking about the use of advanced tools and simple terms to enhance the accuracy, the speed, and the efficiency and the effectiveness of our designs. The objective is clearly defined that we want to streamline the design process. We want to reduce the time, the cost. We want to use the material more efficiently because we have so many limitations at the time being. We have the carbon footprint we are trying to reduce. We have a shortage of budget and most of the projects, and many of our projects are tight on schedule, cost, etc. So this explains the need why we needed to dive deep in automation and optimization and geotechnical engineering and numerical design. So whether you are expert or not, I'm not claiming I'm expert at all in artificial intelligence or machine learning, but to some extent, whether you like it or not, whether you are expert or not, you will need to utilize it because nowadays they are becoming indispensable. After this introduction, why is that the case? So the need for this tool or this technology arises from the complexity of the soil or of the ground in general. We are dealing with non-engineered material. It is non-linear, heterogeneous. The materials make the materials we are dealing with is extremely difficult to model or to simulate its behavior with even with the most advanced tool we have. We are not claiming that we reached a level that we fully understand the soil. We are predicting and estimating the behavior of the soil. So this complexity makes our design and numerical simulations usually requiring some efforts of sensitivity analysis, of trial and errors and uncertainty. So that makes the process of the design slow, repetitive, and of course it is a human error prone. Also for the efficiency, the automation cuts down the repetitive task, as we said, and frees up the critical design time, because instead of spending times on the repetitive task, we can focus more on the critical aspect of the design and try to understand the implication of the problem we are dealing with. So the development, it didn't pop up out of the blue. The automation and the machine learning, it developed and passed through different stages. It evaluates or evolved from a manual, completely manual methods and analytical methods to semi-automated with the advancement of the software, and now we are in the era of the fully automated design or system. There are certain softwares or numerous software available in the market today, like Plaxis, Black, etc. They start to offer built-in automation and optimization tool because they realize it is becoming indispensable tool to help you manage your time more effectively. We are also talking about the BIM integration nowadays, which combines the geotechnical design with the other type of data to help us manage the project more efficiently as well. And we cannot talk about numerical design and about automation and optimization and next generation without the touch of artificial intelligence and machine learning. I'm sure Dr. Dana today will have more to say about this, but briefly saying that the machine learning in geotechnical field can help us to predict the soil behavior, optimize the design, and enhance our simulation, while the artificial intelligence automates the decision making and identifies the optimal solution. All combined will provide us with data-driven design or reality-based or performance-based, call it whatever you want, designs, which enhances the real-time monitoring or semi-real-time monitoring and adapts to site conditions. The advantage as we go through this, you may realize that it relies on the accuracy, it reduces the errors, the human errors, the repetitive errors, it improves the model precision, it saves the time and the cost, of course, because with the sensitivity analysis, with the optimization algorithms and techniques, we are ensuring our design are optimized, and also the adaptability, because when we are talking about reality-based design and real-time data monitoring, we are adapting to the site changes and conditions. However, there are some challenges and limitations, but with the advancement and sources today, it's becoming more and more easier. The data quality, artificial intelligence and machine learning depend on high quality data and the amount of data needed as well to train your model. The complexity, the advanced tools need, of course, specialized expertise and training. The initial cost might be high at the beginning, but absolutely it is worth it. And that's why if you are trying to get into the AI and machine learning and automation just for sake of automation, then don't do it. But of course, if you want to utilize it to help you manage your projects and designs better, then for sure this is the tool for you. What is then in the future, or the future trends, is the IoT, Internet of Things integration. We are talking about real-time data acquisition and adaptive design. This is trending at the moment, and this is where the next generation geotechnics is heading. We are also lack of proper standardization in the industry and code of ethics for the automation and AI and machine learning. There are also trending research which focus on the artificial intelligence, machine learning, and unsupervised learning and deep learning. I hope my colleagues today will shed more light on this. Also, we need continuous education and training and improvement to comprehend this computational tools combined with the AI and automation. Let me show you now, walk you through a real life case study for a completed project we have done. This said to be in Bahrain and said to be the world's largest microbiome draft project, where we have installed like 12,000 microbials and post-tension blast foundation over 70,000 square meter. So this is a real project. It was designed and analyzed with the help of the artificial intelligence, automation, and optimization. So in this graph, for example, every dot in the point is a 3D numerical model which contains more than 10,000 microbytes at least. So each point is a model, and we are performing sensitivity analysis to identify the most optimum number and spacing and distribution of the files. So you can imagine without automation and optimization, what are the difficulties and how long it will take from you to run these analyses and to come out with a conclusion out of it. Similarly, for the mesh sensitivity analysis, we have different size of the meshes, different finance and coarseness factors. So we are identifying also the best fit or the optimum size of the numerical mesh. Now, also, when we are dealing with the microbytes and advanced numerical model, we have, for example, for some of the numerical models like hardening soil model, more than 13 or 14 soil parameters or soil model parameters affecting the response of the microbiome. So if we have a monitoring data or a microbiome load test data, and we want to back calculate or calibrate our model based on this data, we need to identify the most influential parameter and how to change them and what are the impact of each parameter on the response of the microbiomes. So we performed a set of support vector machine, artificial intelligence, and machine learning tools or analysis methods, and we identify the most influential parameters. This is, for example, the artificial neural network. And based on that, you can see the mesh is taking the major part of the influence on the response of the microbials, and there are other parameters as well. So identifying these, we developed an optimization algorithm that can back calculate and calibrate the numerical model based on the pilot test, for example, or let it be plate load test or INSAR data or monitoring data, whatever data you want to utilize. So we have developed this algorithm, and in approximately 30 to 45 seconds, it will give us the optimum solution, the best fit between the numerical method and the geotechnical data. And as you can see, the black dashed line is the numerical result compared to the green and the red, which are resulted from the feed. Similarly, we have developed an optimization algorithm, also automated as well in Blacksys 3D, to optimize the location of the piles. At the moment, we are working only on the location, but it can be expanded to take into account the different diameter, different length, and or depth of the piles. So here, just for sake of an example, we have inserted a raft on piles or pile draft with piles on a certain location and the load in another location, and we perform our optimization algorithm to identify or locate the most optimum location of the piles underneath the rafts. You can see this is the algorithm. Each point is an analysis or a model. And in a reasonable time, we have converged to the optimum solution, as you can see. And these are the piles after it changes its locations. Another method also, another optimization and automation I want to shed the light on is in determining the modulus of subgrade reaction, as you can see in the video. Yes. So as you say, as you are aware, there are many methods to determine the modulus subgrade reaction. The conventional methods, which has inherent limitations and challenges and issues out of it. The second is partially coupled soil structure interaction, where we are determining the stress and the settlement from the geotechnical model, and then we are converting it into modulus of subgrade reaction, and this can be done using the automation and the coding technique to reduce the time, and because it is a repetitive task and you need to get the results more quickly, whether it is raft or piles or isolate things, you name it, you can get it. And the most interesting part is method 3, which is the fully automated or fully coupled soil structure interaction, where you can appreciate really the sense of the automation. I hope I am on time, but I need just 2 minutes approximately. So you can see this is the raft and this is the bile modular circuit reaction, but this is what we are talking about, the fully coupled and fully automated soil structure interaction, where we can significantly reduce the time required to model a full structure, taking the full structural elements and properties and loads into our geotechnical model and export the result or the deformation analysis result back to the structural model in a fully integrated method, which again enhance the accuracy, enhance the safety of the design, enhance the utilization of the material, and eventually will yield an optimum design solution. So based on that, we developed also a simple tool to automatically convert the analysis result of the deformation and the stresses and fluxes into modulus of circuit reaction instantly using Python, of course. So just a simple tool with a minimum interaction required by the user, and you can see the modulus of circuit reaction plot immediately at your fingertips. So what is the result? We have completed this first phase of the project 2 building. You can see 2 towers, which we have shown. This is the settlement plots, and we also monitor it with some settlement cells devices. And you can see a reality-based, or let's say performance-based design, where the real-time deformation matches well or in agreement with our prediction and simulation. That's it from my side. Thank you, and hopefully I didn't take long time, Ahmed. The stage is yours.
You're inside. Thank you, Hamza, again for this precious presentation. And I will invite Omar Alawi, Engineer Manager in Maritime and in Geotechnics, to present leveraging big data for enhanced decision-making in maritime geotechnical engineering. So Omar, the floor is yours. You can share your screen.
Hi, thanks, Ahmed. I will just turn off my camera during the presentation. And thank you, Hamza, for the nice presentation. I will now share my screen.
Yes, can. Yeah, just before you can start, you can just make a brief summary of your presentation, and before that, a mini CV of your distinguished career. So Omar Alawi is a distinguished civil engineer with extensive expertise in the maritime industry. He holds a master's degree in civil engineering of large energy structures from École Nationale des Ponts et Chaussées et l'École Centrale Paris in France, and an engineering degree in civil engineering from École Hassania des Travaux Publics in Morocco. He is also a certified project management professional and holds a project management qualification. Currently, he is serving as an engineering manager for ADNOC L&S, leading the engineering scope of a $1 billion artificial energy island project in Abu Dhabi. With a robust technical and practical background in geotechnical and maritime engineering, Omar has successfully managed numerous high-profile projects across the UAE and the UK. Previously, he served as a project manager and lead maritime engineer at Royal Haskoning in London, and geotechnical engineer and engineering manager at the National Marine Dredging Company, NMDC, in Abu Dhabi. In addition to his current role, Omar is the co-founder of an engineering tech startup focused in developing bespoke smart software aiming at leveraging big data for enhanced decision making, driving innovation and technological advancements in dredging, reclamation, and marine construction works. Omar Alawi has contributed to the design, development, and delivery of over 40 artificial energy islands, mixed-use waterfront developments, and port projects. Omar,
thank you very much, Ahmed, for the presentation. Yeah, I will carry on with my with the second session. So first of all, thank you very much for organizing this webinar with reputed speakers, Mr. Hamza, Dr. Rodena, and Mr. Philip. For myself, I will be speaking about leveraging big data for enhanced decision making in the maritime geotechnical engineering with some applications in maritime projects. I know that we have only 15 minutes, so I couldn't. I mean, I will try to make my presentation within these 15 minutes, so we will not go into, let's say, a lot of details. I was starting by an introduction, defining big data in the maritime geotechnical and how big data is important for the maritime geotechnical engineering. I'll be speaking about some applications in land reclamation projects, hydraulic field projects. Then with a case study, then I will be speaking about some applications in breakwaters with a case study. Then quickly go through challenges and solutions, and then I'll be concluding with some recommendations for further readings. So always referring to BS, British standards, defining big data. BS 10102 defines big data as extensive data sets, primary in terms of data characteristics. We are talking about volumes, variety, velocity, variability, the famous 5 V's. We have also 2 V's to add for our industry and mainly also for geotechnical engineering. We talk about volatility, which means time span in which data values remain relevant. Sometimes they are not relevant anymore. So, and then validity. So we're speaking about specified data format. So data should respect specified data format for, let's say, smooth processing. So big data requires scalable technology for efficient management. I mean, we cannot basically deal with this big data using Excel, for instance, or simple techniques. So mainly we would be using programming languages such as R, Python, MATLAB, or or other techniques. Big data is important, definitely for our industry, for the geotechnical engineering, modern geotechnical engineering, where it can drive innovation and efficiency in design and construction. And also it enhances decision-making processes, reducing risks, and allowing for let's say a stronger control over the construction of let's say duration of project, and as well during post handover for asset management, for example. Big data also enhances our understanding of geological conditions, let's say, and it supports informed decision making. I'll be giving some examples later. Data sources in our industry, in the geotechnical / maritime industry, we do use feed testing data, comp penetration, standard penetration test, pressure meter. We use also lab test data, chemical tests. We use imagery techniques or technologies. We can use cameras, drones, UAVs, ROVs, LiDAR, INSAR techniques. We do use also data from geophysical sounders like single multi-beam sounders, sub-bottom profilers, magnetometers, and side scan sonars, etc., etc. In terms of applications in land reclamation projects, so by land reclamation project, for this presentation, I'm mainly referring to artificial islands, but also to waterfront development, ports, mixed-use developments. And wherever I refer to data here, it's mainly big data because in our industry, we deal with, let's say, big or large data sets of data. So data for us is, usually referring to big data. In terms of applications in land reclamation, so big data or by using, it can be used in different manners. Let's say we can use it for a better project planning, let's say, by using real-time data to check against the baseline schedule, our resources, timeline, etc. We can have an enhanced or stronger project control, and we can even let's say adaptive project planning where we can make changes, but with the supported by information that we get from the real-time data that we are getting throughout the project, not only before the project during tender phase. It is also helpful for project control and monitoring. So continuous data acquisition with ongoing data analysis. Mainly I'm referring to wherever we have smart techniques, smart systems, smart software to directly acquire the data and process and provide dashboards and with insights, with regressions, with early warnings. It helps identifying and addressing geotechnical non-compliances. It helps reducing risks. It helps us take informed decision basically and have an enhanced project, let's say enhanced monitoring during maritime civil projects from geotechnical perspective, at least. It helps us as well carry out some value engineering and come up with some value engineering proposals, VEPs. With data-driven decisions using real-time monitoring would allow us for systematic processing. We can set up the way how we want the data to be processed depending on the data type. For example, CPT data before ground improvement and CPT data after ground improvement. And then adopting, let's say, our ground improvement techniques for artificial islands project and reclamation project, where we can optimize on the ground improvement even before going and doing the ground improvement, achieving the required performance at lower cost, basically reducing the CO2 footprint and allowing to both the contractor and the client to finish on time. It helps as well in the project simulation. This is mainly referring to tender stage before award of the project, where we can make use of the acquired data to model and predict project outcomes, and use the outcome of this simulation in the tender, let's say, preparation, where we will have more control over the risks and opportunities as well, and then we would price properly. So how this can happen? So wherever we apply or we acquire data during project that we have, we can store this data, process it, and structure it, let's say, and then teach, create, and set up and teach adequate machine learning models. So here we talk about the use of AI for a more efficient future land reclamation design. So we can make use of data that we acquire all the time for the next project, let's say, for a better pricing, for let's say reduced risks, and let's say better design, enhanced design and safety, ultimately, and reduce the carbon dioxide footprint. So here's an example where in a project with ADNOC, Hail and Ghasha, a set of 11 oil and gas projects where we myself have used set of bathymetric topographic data, penetration testing results, borehole data with fines content measurements, carbonate content, shell content, and sieve analysis, along with construction progress data to basically, as you can see on the right at the top, the island, the reclamation area is split into boxes, and where we were controlling, let's say, the quality of the fill during construction, and after ground improvement, we were controlling the quality of the ground improvement, and then not only vertically but also horizontally, but because usually we forget to look at the bigger picture. We only focus on soundings from one CPT or two, whereas it's more important to look at the bigger picture, the area, but also it is important to look at localized issues and let's say make sure that we, let's say, take remedial measures during construction, where it is much cheaper than ending up with lots of problems, embedded problems, a project that is already done, where remedial measures can be very expensive. So the data that I used at that time helped also to come up with the site-specific soil behavior type versus tip resistance correlation. As you can see at the bottom, using a large set of data, millions of points, and basically this helps in future projects, let's say, to quickly correlate between the tip resistance and soil behavior type, instead of going through dozen of equations from the empirical equations, let's say, from the literature to process, whereas sometimes they are more related to other types of sand, like silica sand, where and in our case we have carbonate sand without let's say specific correlations. So we can make use of the data, to come up with site-specific correlations, and then we can also make use of this data to detect uncompliant layers, trends, and patterns. I think I need to move quicker. I still have only 3 minutes. I will try to accelerate. So we have also other applications in breakwater design mainly. So before the project, mainly during geotechnical investigations, let's say campaign, we can use big data, let's say, and big data processing tools for site assessment and feasibility studies, for site selection, the evaluation of the geological conditions and geotechnical conditions, especially wherever we encounter problematic soils with, let's say, long-term behavior. We can use it also for design optimizations, to come up with an optimal design and predict, let's say, using predictive modeling for better outcomes, especially when we can use the data for in sensitivity analysis, in simulations, or in modeling, let's say, in 3D, for instance, for example, using Plaxis 3D. So where a large set of data can be processed quickly and can be input using scripts directly into the model, instead of focusing on instead of working on many sections and spending a lot of time in design. So then we can use it also in construction monitoring and management. Real-time data can help in terms of project management, tracking the progress, identifying issues during and post handover. I'm speaking here about asset management. So big data can help us. Through a set of sensors, settlement plate, for instance, or other techniques, monitor the creep, consolidation in problematic ground conditions. Also, by processing and by looking at data and by analyzing the data, we can check deformations post storms, earthquakes, mainly in large breakwater structures, such as one that I'm showing here is the main breakwater for Tanger Med 2 port in Morocco. 2.7 caisson breakwater with the large caissons, 24 by 24 by 28 meter caissons on top of a thick, let's say, foundation that goes up to 15 meter, where in some areas, as you can see at the bottom right, the connection between the rubble mount and the caisson breakwater, where we found out that we were very close to a river bed with cohesive soils, where we had meters of settlement for the first couple of caissons. And then using data, we were able not to remove everything, but just to monitor and check the consolidation during construction and up to before the handover, where we found out that we reached a good level of consolidation. And then we optimized in terms of construction, using the engineering sense and the processing big data, we found out that the structure was stable at the end, after a couple of measures that we carried out during construction, that the project team basically carried out. So here is a case study where big data is used extensively in Tanger Med 2 port between two caissons. Along the breakwater, we have installed several inclinometers, extensometers, inverted pendulum, and one accelegraph, getting data on hourly basis, let's say, continuously since more than 10 years, and this will continue for another 40 years at least, hopefully. So this data is I will be speaking here about, for example, extensometer that you can see here on the right top picture, where we can monitor the XYZ deformations of between two caissons, and also the temperature. And this basically helps tracking the movement and detect patterns if there is anything let's say abnormal happening. It also helps in predictive maintenance of one of the port critical structures, which is the main breakwater. You can see at the bottom right an example of the measures between well, this is from this is an example from Tanger Med 1, 2006 to 2015. So where we can see sorry, this is from Tanger Med 2. Apologies. Just the month of December, where we can see the XYZ movement, and you can probably observe that the Y movement is a bit more important. This is mainly due to the tidal changes and the wave action. Challenges and solutions. There are a few or many challenges and solutions in our industry, and where we need to engage stakeholders and to allow for a budget for instrumentation programs, let's say within projects, for acquiring site-specific data, so that later we can use it, invest in smart data management systems during and after construction, so that we can proactively manage the assets. Then another challenge is the data quality and integration. We need to make sure that the data that we are getting is reliable. We usually have lots of problems with the data that we get from field testing. So it is important to make sure that data is reliable before doing any processing or setting up any machine learning models. Otherwise, it will be useless. Then we need to try to integrate all data sources and then come up with insights. So we don't rely only on one source. We can combine a couple of sources before deciding. And then from technical and operational point of view, we need to invest or let's say make sure that we have adequate handling equipment to handle large volumes of data. And then using offline servers or cloud computing, depending on the client or stakeholder, and let's say the type of data. And then so invest in technical infrastructure, in teams, and in training. So to conclude, so we have spoken here about big data, have defined big data based on PS. We spoke about example from the use of big data in land reclamation, and also the use of big data in breakwater design, optimization, asset management, let's say monitoring post handover. I would recommend to check the BS 10102 part 1 and 2 for the guidance on the data-driven organizations and guidance on data-intensive projects. So it promotes good practice within organizations and teams. As you can see here, it covers structures, governance, organizational needs, project definition, project management, project delivery, how we can make it with the use of big data. And that's it from my side. Thank you very much.
Thank you, Omar, for this interesting presentation. We are a little bit over time, but it has the merit to break some couple of questions, which we'll be happy to answer at the end of the presentation session. So there's a Q&A session after the presentation session that will be held at the after the presentation session. I'll be happy now to introduce Dr. Dana and make a brief summary of her presentation. Dr. Dana, the floor is yours, and please share your screen so I can start presenting. Yeah.
Okay, you can see my screen?
Yes, thank you.
Okay.
So Dr. Dana Abul Husn is an academic and entrepreneur with a diverse background in academia and industry. She is currently assistant professor of geotechnical engineering at the Australian University in Kuwait and adjunct research fellow at Curtin University in Australia. She received her bachelor degree in civil engineering from the Lebanese University in Beirut, Lebanon, and the Master of Science in Geotechnical Engineering from Lille 1 University, Science and Technology in France, and a PhD in Materials and Mechanics and Civil Engineering from Grenoble-Alpes University in France. Driven by a passion for innovation and technological advancements in the construction industry, Dr. Abul Husn is the visionary founder and CEO of Construct Tech Services, headquartered in Dubai. She will be presenting an overview of technologies revolutionizing geotechnical engineering which will be provided, including advancements in AI, digital twins, and VR and ER. The application of AI in geotechnical projects will be explored through case studies that highlights its impact on predicting patterns and enhancing decision-making. Additionally, common misconceptions about AI and geotechnics will be addressed, clarifying its role and potential. This session aims to illuminate the transformative power of AI and machine learning and correct misunderstandings surrounding their implementation in the field. Dr. Dana, please go ahead.
Thank you. Yeah, good morning, everyone, and thank you, Ahmed, for the introduction. I'm so happy today to be part of this webinar and to share the stage with great minds, great speakers. I will just close my camera during the presentation. And so let's start. I'm very happy today to present a topic that I'm very passionate about. It's about the applications of AI and machine learning in geotechnical engineering. So, in fact, in this presentation, I'm going to start with a brief overview of recent technologies. I will not talk about details of the current technologies used, and already the previous two speakers, they spoke about some of the technologies. I'll just shed the light on other new concepts. And then I will follow that by applications of AI and case studies in geotechnical engineering. Here, I will talk about only mainly one type of machine learning algorithms, which is artificial neural networks. I will not present the technicality of the method. I will just present some results of applications and case studies. And after that, I will talk about some misconceptions about AI that are limiting the applications of AI techniques in geotechnical engineering. And finally, I will end by some key takeaways. So starting with an overview of recent technologies. In fact, today we are living in a world where we can't escape new technologies. Some examples of the new technology trends include digital tools like 3D modeling, virtual reality, augmented reality that enhance the design and visualization of projects, and they can provide immersive experiences that can help in decision making and others. And also we have among the technology trends advanced monitoring systems such as IoT, as presented previously, IoT sensors, or for example, LiDAR or satellite monitoring, which help in enhancing the maintenance of geotechnical structures and predicting any health issues in the geotechnical assets, and also improving the lifestyle of the geotechnical assets, and also automation, as presented also previously in previous presentation. So automation, whether through robots or other techniques, it is also minimizing the time, reducing the risk on construction sites, and we have data analytics. Now, when we talk about data analytics, at the core of this new technology, we have artificial intelligence and machine learning, which can learn patterns and help in predictions and decision making. So if we use all these technologies together in one system, we can create a cycle of processes, which then we can call them a digital twin. A digital twin, in fact, it is a virtual replica of a real asset, which consists of the different tools that I just mentioned. In fact, we'll have a model, a 3D model that allows us to visualize properly the geotechnical asset. We will have advanced monitoring tools to monitor and predict what will happen to that asset. We will have automation that can help in the design and analysis or in the operation of the structure as well, and automate all the cycle. And we'll have data analytics in predicting future trends in the geotechnical asset. So all these can create the digital twin. Now, in this presentation, I will just concentrate on one part, which is the data analytics and mainly AI. And when we talk about AI, there are different techniques in artificial intelligence. One of these techniques is using machine learning algorithms. And there are many machine learning algorithms, such as genetic programming, artificial neural networks, recurrent neural networks, and many others. The simplest method, I would say, it is artificial neural networks, which imitates the way the human brains process information. And in this method, in fact, what we do is we try to model a set of artificial neurons connected together, and they transfer and process the information similar to the way that human brains function. So I will not explain the technicality of the method, but I will concentrate more on the applications. And here, the applications that I'm going to talk about, they are fundamental applications. What I mean by fundamental applications, I will compare, for example, how we can use ANN or RNN I will compare it with the empirical traditional methods that we currently use in geotechnical engineering. Or, for example, how we can use this method to generate an AI-driven constitutive model, or how we can use this technique to just find an equation, a functional equation that can link some parameters with an output value. So this is what I call it a fundamental use of AI or machine learning algorithm in geotechnical engineering. So let's start with some applications or case studies. The first application that I will talk about, it is the prediction of settlement of shallow foundations. In geotechnical engineering, we have lots of data, whether from field tests or from laboratory tests. So we have a huge amount of data. AI can help us in transforming this data into a kind of knowledge. So here in this example or in this application, what we used is we used a data set that consists of 189 individual cases of field measurements of settlement of shallow foundations. And the data that we use, it covers a wide range of variation in footing dimensions and cohesionless soil types and properties. And we developed an artificial neural network. And then we compared the results obtained from the artificial neural network, which is the first figure here, with other empirical results from empirical methods like Meyerhoff, Schultz, and Sheriff, Schmertman. And you see here also there's a table that shows the performance or the metrics for each method. And as you can notice, the artificial neural network, it allows us to predict the settlement somehow accurately compared to other empirical methods. And the prediction, it's not only for small values of settlements, it can predict the settlement, a wide range of settlements, from small to large values of settlements. However, the other empirical equations, you can see here in these figures, they can function accurately at low values of settlement, and they diverge when the settlement is very high. And if you see the metrics here in this table, you can see that the performance of artificial neural networks is better than the other empirical traditional methods. So this means that artificial neural networks can even outperform traditional methods commonly used in geotechnical engineering. Now, another application, it is the prediction of the full load settlement curve of pile foundations in Dubai sedimentary rock. In this project, in fact, we gathered data from the business bay in Dubai. So we gathered about 116 data of 116 static load pile tests obtained from more than 45 towers in the business bay and downtown Dubai areas. And we developed a recurrent neural network because we are here predicting a full curve. So are treating this type of data as a sequential data. And I'm just going to show preliminary results. We are still working on this model. So these are just some preliminary results to show the measured versus predicted load settlement curves from the recurrent neural network and the field tests. And as you can see, that the performance of the model is very, very high. And the model is able to capture accurately the field behavior, the sedimentary rock behavior. And what we are going to do, in fact, in this project, we are going to create a simple application which allows engineers to use this model easily. So are creating a simple user-friendly application which would consist of just asking the user to provide the inputs, which consists of the geometry of the piles and some properties of the rock, and then they can get the load settlement curve. In fact, doing that, it means that on-site, we can now reduce the number of tests. Instead of doing too much tests on site, we can just reduce the number and therefore reduce the cost in any project. Another application, it is the prediction of the mechanical behavior of railway ballast. In fact, here the objective of showing this application is just to compare with commonly used constitutive models that we usually use in commercial softwares, for example. So in this application, we gathered a data set which consisted of 29 large-scale triaxial tests, drained compression tests, and they were conducted on different commonly used types of railway ballast. And we developed also a recurrent neural network so that we can predict the full curves of the deviator stress versus axial strain and volumetric strain versus axial strain. So in this slide, you see the results from the recurrent neural network and the results from a commercial software Plaxis using the hardening model. So the finite element model, it gives good results. The predicted curves, they fit well with the measured curves, and the recurrent neural network, it does the same. In fact, we have the same results. The AI model is able to predict the hardening, the softening of the ballast, and also the dilatancy or the contractancy of the ballast. So compared to the FEM model, recurrent neural networks are able to give similar, accurate, and maybe even more accurate results than a traditional constitutive model. Now, what's interesting in this application is not the application on a monotonic and simple loading path. Here in this example, I showed only a simple loading path. What if we have a very complex loading path that we need to model? If it is a very complex loading path, this means that we will need a constitutive model that is also, it will be also complex. And more complex, it means that we'll have more parameters in that model. And more parameters, it means the calibration of the model will be more complex as well. It will require more laboratory tests, more field tests to calibrate the parameters. So why not use recurrent neural network to develop an AI-driven constitutive model, mainly to be used not on simple loading paths, but on complex loading paths. So that would be one of the benefits, let's say, or interest. It will not need more time and effort to calibrate this model as it will be the case for complex constitutive models. The last application that I will talk about, it is the prediction of the effective stress distribution in internally unstable soils. Internally unstable soils, I mean by them the internal erosion that takes place in hydraulic earthen structures such as embankment dams or levees, for example. So internal erosion, as a definition, basic definition, it is the loss of soil particles from a soil matrix. And there are different types of internal erosion. One of these is called suffusion. I'll need just to present the definition so that you can follow with me the results that I will show later. So suffusion, it means the particular erosion of very small particles in a soil matrix. So we call them fine particles, but not necessarily clay or silt. It can be just the relative size of there will be modifications in the porosity and the hydraulic conductivity of the soil, and this might lead to degradations in the mechanical behavior of the soil and eventually to the collapse of the hydraulic structure. So usually what we do as geotechnical engineers, we try to assess if a given soil is susceptible to suffusion or not. And to do that, we follow different criteria, either geometric or hydraulic or stress criteria. Now, when it comes to geometric and hydraulic criteria, we already have many methods that we can follow. However, when it comes to stress criteria, the problem becomes more complicated because during suffusion, in fact, what happens is the coarse particles, they form a matrix that is mainly responsible of transferring the stress in the soil matrix, leaving behind the fine particles, the smaller particles under lower stress, which makes them more susceptible to detachment and migration. And therefore, in order to analyze this problem and to develop a stress criterion, we need to understand or to calculate the fraction of stress that is transmitted by the fine particles. And this can be done, for example, using the equation given by Scampton and Brogan, which is in fact, alpha here. It is the factor which is called the stress reduction factor. It is the ratio of the effective stress transferred by the finer fraction to the overburden effective stress. So to calculate alpha, we need to have information at the micro scale of the particles, and usually this is not a very easy job to be done. So usually what we do is we try, for example, one way is to develop a discrete element model, because this problem would require a microstructural analysis. So if we develop a discrete element model, which usually consists of modeling an assembly of granular particles that are connected together through interaction laws, and this will allow us to access information at the particles scale. So in this, however, in fact, the discrete element model, it requires a high computational time. And especially if we are working with wide-graded soil, or very well wide-graded soils, this would require a high number of particles, and therefore it will require a high computational cost. So what we did, in fact, in order to replace the use of this method, we tried to develop an AI model. And in this AI model, it is an artificial neural network, a very simple artificial neural network. We ran different simulations using different particle size distributions. We ran around 124 simulations, which took too much time to get the results. And then we used these results to develop the artificial neural network. For the artificial neural network, we used input parameters as D15 over D85, which represents the diameter of 15% finer fraction of the coarse fraction divided by the 85% finer diameter of 85% finer particles of the finer fraction. We also included one input parameter, which is the fines content, which is the amount or the percentage of fine particles. One of the inputs is the gap ratio and the void ratio. In fact, we chose these parameters based on the literature, because already there are some studies done that show that these parameters are or influences the stress transmission in the finer fraction. So we used these model features, and we created the artificial neural network, and we obtained a good fit of the results, the predicted versus the measured, and with a high performance coefficient of determination of 0.92. And what we did, we tried to transform this model into a simple equation, which relates alpha, the stress reduction factor given by Scampton and Brogan, with the model features that I already presented. So this simple application substitutes the use of discrete element model, and instead of taking too much time to get the results from discrete element model, it is enough just to use this simple equation, and then to follow a stress criterion, which consists of some limits that we can define for alpha to know if the soil is susceptible to erosion or not. So these are just some main applications. And now what I'm going to talk about is that, okay, what I presented, it is the applications at a fundamental level. But these applications, they have lots of limitations in geotechnical engineering. And these limitations are due to some misconceptions about AI models. So I would like just to shed the light on some of these misconceptions, address these issues, and show some myths versus realities. So the first myth is that AI models, they are blamed to be black boxes. Especially when we talk about artificial neural networks. In an artificial neural network, if you are familiar with this method, usually artificial neural networks are presented as layers of neurons, virtual or artificial neurons, connected together. And this usually gives the perception that this model is a black box. We don't see equations. Unlike, for example, constitutive models, where we see equations, it gives a more scientific sense. So this results in this myth that AI models are black boxes. Well, in reality, In reality, AI models, they provide clear and functional mathematical relationship between model inputs and outputs. That's what I showed when I just presented the equation, for example, of alpha. There is a clear equation, functional equation, that relates inputs with outputs. So AI models, they are not black boxes. Now, another myth is that AI will eliminate the need for human judgment. And this is not true. This is wrong. AI will just support a human judgment. And in any model, whether it is AI or other model, will always need the human judgment. So it's just a support. It will never eliminate the need for human judgment. Another myth is that AI can only be used for large-scale projects. Usually small companies or medium-sized companies, they think that they don't need AI because they are not working maybe on big projects. And the reality is that whatever is the size of the company or the size of the project, AI can benefit or can benefit projects of all sizes, whether it is at the scale of project management or at the scale of design optimization. AI can be used at all levels. And another myth is that AI is too complex and expensive. And the reality is that AI solutions are becoming more accessible. Maybe at the beginning, AI tools were more expensive, but nowadays AI solutions are more accessible. The last myth that I will talk about is that implementing AI is too disruptive. Some companies, they think that if they implement AI in new technology in their company, in their team, that this can disrupt their work. And the reality is that AI integration, it's not necessary to be sudden. It can be gradual, progressive. So companies can implement or integrate AI step by step. And that's what we do. In fact, in my company, Constructive Services, we try to help other companies to integrate AI gradually so that they avoid any disruption. So finally, some just key takeaways of AI-based solutions in the geo profession. So I've shown some applications of how a data-driven tool, AI tools, can help in decision-making, how it can outperform traditional methods, and how it can be used as to develop constitutive model, and how it leads to design optimization, it increases efficiency, and it leads to smarter and more sustainable infrastructure development. Thank you.
Thank you, Rodina, for this presentation on AI, and thank you for correcting the misunderstandings surrounding their implementation and showing that it could happen progressively. Now I'll invite Philip to share his presentation.
Yep, sure.
Yeah, thank you, Philip. Before you can start, I'll make a brief presentation of yourself. So Philip has extensive experience in providing design and technical support for a variety of projects, including those in the roads, railways, bridges, and tunnels sectors. He specialized in geotechnical analysis and design, utilizing finite element packages such as Plaxis 2D and 3D, leapfrog, strand 7 slope, rack science packages, and limit state geo, etc. Philip is passionate about innovation, challenging traditional approaches, and discovering new methods for engineering and designing structures. He has developed automation tools using Python to enhance the efficiency of design workflows. Recognizing the versatility of Python, he has focused on creating content to share its benefits with the civil engineering community, particularly in areas such as Python automation, AI in engineering, and digital transformation. Today, he'll be presenting Python automation in geotechnical engineering and tunnels. Philip, go ahead. Thank you.
Okay. Thank you, Ahmed, for the introduction, and nice to meet you, everyone. I think good morning to most of you. It's nighttime in Australia. Great presentation from Hamza and Omar Rodina. So for my presentation, I will be primarily focusing on Python automation. So these will be the topics of my presentation. So I just turn off my camera to make it smoother. So before starting it, I think starting with a question, how you feel about your daily work as a geotech and tunnel engineers. To me, I enjoy what I do in design, but I also found there are a lot of manual tasks involved in our industry, like interpreting boreholes, data entry, etc. The intent of this webinar is not to provide new engineering knowledge, but to provide some idea on automation based on my own experience as a early career engineer. So it can prompt you to start thinking about some opportunities ahead in your career. So a bit of myself, I'm a geotech and tunnel engineer by practice, but I'm also a keen programmer. I self-taught and use programming for about 5 years now. So I work on different geotechnical and tunneling projects with a lot of infrastructure exposure. And I use numerical modeling for different infrastructure projects, including PESIS 2D, 3D, Strand 7, Rock Science, etc., as Arman has just introduced. So, but my unique skill is developing automation tools using Python to boost the efficiency of the current workflow for geotechnical design, mainly for our team. This is the table of contents of this presentation. I will first talk about introduction of Python role in engineering. Then I will go through some of the geotechnical design automation case studies. Then I will just briefly talk about the pathway to automation as an engineer. So start with the introduction. So why we want to use programming in engineering? Engineering design involves data inputs and data analysis, which are repetitive tasks. Programming is a perfect tool for completing repetitive tasks. And once the code is built, it can be modified slightly to fit different purposes. So this is called modular engineering. And as a geotech engineers, one of the major skills is numerical modeling. A lot of the software that we use nowadays got API, including PESIS, 2D, 3D, lately Rock Science packages, which allow us to use modeling software more effectively. And it is a future trend, so just emerging trend to utilize programming for different aspects of design. And among all the languages, Python is probably the best candidate for the following reason. It is easy to use comparing to other languages such as C# and C++. It's easy to understand, easy to operate, easy to write. Software API, a lot of software now have integration with Python, which makes us more useful for our field. It's got strong external libraries. It can link to Excel, Word, web browser for all automation tasks. And it's got a strong community. So more and more geotechnical engineers or wider civil engineers are using Python for their daily works. So here's just a list of range of libraries for different use cases that I mainly use for my daily workflow. So I automate engineering software like PESIS, Strand 7, ArcGIS, using Python API, and we don't need to think big doing necessarily a complex numerical model, but we can use Python to automate simple tasks like extracting Excel spreadsheet, doing parametric design using pandas, just exploratory data analysis when we receive a whole bunch of data like CPT, SPT, etc., using a data visualization tools to look at the data, PDF extraction, which I love so much, to do borehole extraction, for example, we can do that. So it just gives you a feeling on there's a lot of application that Python can help us on in the geotechnical field. So here's just some example of the automated designs in worldwide. The design automation is an emerging trend in Australia, Europe, North America, and I'm pretty sure in Middle East is going pretty fast as well. Melbourne Metro Station Cavern Linings, a project in Melbourne, is designed semi-automatically using both Python and Strand 7. A thermal belt tunnel are being built designed using automated optimization algorithm using a platform called Victor, which is also powered by Python. And just lately, WSP automate analysis of ground improvement design using PES's Python integration. So you can see there's a lot of design has been done using automation lately. What are the benefits of automation? It probably can come down to this 4 points. With more rapid initial design and visualization, it can support quicker decision making. Automated design optimization and optioneering can lead to reduction in cost. And of course, if we can use automation, we potentially can deliver a project with a smaller design team, which increase our design efficiency. And lastly, it got more time available for us engineers to focus on challenging high risk and high gain items. So what is engineers' role in digital era? What our role in this era in the automation field. So as an engineer, we need to learn to think, design in the system and create process. And we need to learn to delegate to software developers or AI for them to do the automation task instead of us doing that. We also need to learn to review and give feedback to software developers and AI and elevate themselves and work on designing the playbook, not actually doing it. One lesson learned throughout this journey of automation is I feel like this is not for everyone, and you can only do it if you like it. And what I mean here is doing the actual programming. But as an engineer, as I mentioned, you don't need to know the programming, but you need to know how to think in a system and create the process for someone that like programming to create the automation tools. AI such as ChatGPT Cloud has made development easier, though it doesn't mean we don't need to understand programming. So we still need to know the basics so we can communicate and provide guidance for the automation development. So let's move on to some of the case studies that I prepared. So first one is the first project that I apply Python, and this is how the whole automation journey start, which is around Excel data extraction from lab test results. This is a Australia project. What happens is we got a significant movement observed at one of the retaining wall 3, and we just keep seeing continuous lateral movement inward toward the excavated station box, and the delivery team is concerning it could be because of the random fracture rocks across the western wall. So what happens is there are 300 anchors that has been installed along this wall, and we want to assess whether they are performing well and what are the potential cause of the movement. So the problem of this task is it's got very tight assessment time frame, but we need to analyze 300 anchors data, raw data from lab test results from the scratch. So we need to provide high-level assessment to the retaining wall design, assess if the anchors and piles are socket into rock class 3 or better, and this requires assessment of the anchor performance through the anchor test analysis. So the problem is there are more than 300 anchor test report, which you can see in the format on the right-hand side, which are individual PDF. And normal way of doing this is copy paste the load and displacement of each report to another Excel and manually plotting each data set. So that's, as you can imagine, very time consuming. And back then, I don't want to do any copy paste for 8 hours sitting on the chair and doing that. So I asked my team lead and say, can I spend one night just try to write some code for this task? And this is how I started the automation. So the solution is I use Python to extract data using PyPDF2 to extract this data from PDF and summarize in the table and plot graph. So one key message here is that we need to think about the logic flow. Instead of writing the actual code, we need to break down the problem into small components before actually writing it. So for example, in this particular task, what we basically want to do is to scrap all the Excels in the same folder and then convert these Excel sheets to CSV, read the lab test result and store each data set as a list, and then combine them, all the lists, and combine them in the table and export as a Excel. So we can then use that Excel to do our data visualizations, which I will show in the next screen. So this is the final outcome. On the right-hand side, you can see the plots of the result from all the test reports. We can visually see how many of them is moving more than the elastic displacement, and which means the rock is not holding the anchors. And also, what other good thing is the name of each anchor is also generated automatically. So from the plot, we can see which anchor is moving more than it should. So you can imagine if we need to do it manually, that would be a massive manual task. And also, after this task, I actually got more anchors results coming in, and you can imagine I can just reuse my code and do the same task. If I'm not spending time to write the code, I probably end up doing the same task, same 8 hours to finish the task. So this is probably the key takeaway on using automation in your daily tasks. Nothing big, not machine learning, but it just help to make your workflow more efficient. Next one is what I love a lot is process automation. A lot of you here is familiar is Passes, what we use as a everyday software as a geotech engineer. So the ultimate goal is to automate Passes 3D modeling. Why we want to do it? Because usually Passes 3D setup time can be long, and the output extraction are repetitive processes, very time-consuming process because it involves iteration of variables to meet different design criteria. So how do we interact Passes with Python? So I just use a Python analysis in multi-layer soil as an example. So one of the most common designs in geotechnical engineering, and it's contain repetitive elements and material. It's require multiple iterations and it's heavy manual exercise to just do different pile case. So similarly, I use Python to connect to Passes, collect all geometry information from the Excel template, and then use this information to build model automatically and extract results. And again, what important is we know what task that we are aiming for, what are the logic flow to build these tools. So here's the outcome. Let's look at the video. So basically, this code is basically the heart of the automation that it read values from the Excel spreadsheets, and then it start building a Passes 3D model automatically, doing all the structural elements by itself, and then of course the meshing, the staging, and also just running the analysis as well as extracting the results. So you can see we have been doing this manually a lot, but there's just a tools available that you can do this whole process automatically. So a good example on how we can automate Passes just purely using Python. And you may ask why we need to do this, what are the benefits? So just this is a work in progress project, but one application is machine learning. It can automate the process of iterating pile diameter length to meet design requirement. So in using this script, I generate 3,000 Passes 3D models, and the full process by human takes at least 15 minutes per model. So you can imagine that will be an engineer without sleeping, eating will take 31 days to complete this model. But more than that, with Python, the result I get in a needs format, as you can see here, get all the displacement, shear force, Young's modulus, etc. So we can then plug it into a machine learning. So I don't want to spend too much time on this because Modana has done a great presentation on machine learning already, but you can see we can use this kind of tools, build a large data set, and can ask other machine learning expert to do a good machine learning model to predict pile diffraction, for example. So just very lastly, current landscape of automation, we are focusing a lot on complex structures using BEAM, advanced optimization using machine learning, and complex structures are project specific and hard to standardize. But something that we haven't paid enough attention is relatively simple geometry and repetitive optimization, like pile retaining wall geometry optimization, which we can put automation in, which fits quite nicely. So just aware of the time. So I probably skip that that bit. But what I want to mainly talk about is in order to implement automation in our field, it's a collaboration between the junior engineers and the management. So engineers don't need to write code as good as programmer, but need to think like a programmer. We need to think the logic in the design and have the capability to turn it into a workflow, and just challenge the lumps and just ask if you can try things. And in terms of management, they can act as an important role to drive design automation, but it's need to recognize the values and allocate time for junior engineers to conduct trial, prepare for the possibility for unsuccess. So those are just insights. Python can allow automation for different software. And I just want to say this last word, key message is we are not trying to do our design quicker, but it's about using the same amount of time to do a better design. Code can be reused for various applications and even discipline. This means we can be more efficient day by day. And this is the end goal of automation. Okay, that's all. Sorry for the
Thank you, Philip.
overtime.
Yes, thank you, Philip.
Yes.
We're already over time, so we'll not be able to open the Q&A session. Sorry for that. We'll be answering your questions on our LinkedIn page or group. So I invite you to check our LinkedIn page by the end of the week. Thank you again for the attendees, for our esteemed guest speakers. As we dived into today's topics, we've explored how cutting-edge technologies like AI and Python are transforming the landscape of geotechnical engineering, from automation complex analysis to enhancing decision-making processes. These tools are shaping now how we approach engineering challenges in our field. But one last word, keep it simple. Thank you again, and see you next time.
Thank you very much.
Thank you.
Thank you. Bye.
Bye. Thank you all.